Hi everyone and welcome back. Today we're going to talk about the Penrose diagram. So before the video starts, I advise that you adjust the playback speed probably to 1.25 and let's go. So Penrose diagrams. Just before talking about Penrose diagram, I need to introduce a little mathematical prerequisite, which is a conformal map. So conformal map are functions that locally preserves angles. So locally preserves angles, and they are very helpful to visualize infinity because we're mapping infinity to finite point. So an example of conformal map, if I take a conformal map of an infinitely spread sheet of paper, it will be mapped to a single point. Yes. All right. So Penrose diagrams are the result of a conformal spacetime map. So conformal spacetime map preserves relative speed. So preserve wait a minute. Yes, preserve relative speed. And it does that by mapping light rays onto light rays. Mapping LR for light rays. So mapping light rays onto light rays, which we can write like this. ds square is mapped to ds prime square equal a function of the coordinates square times the old ds square. Okay. So Penrose diagram is the result of a conformal spacetime map, and it will preserve relative speed. And we can visualize it as is. So imagine the spacetime S, the conformal map F, and usually the target space is Minkowski. So I will put M. And if you're mapping S onto M with a conformal map, this is how S will be visualized in the target space M. And those boundaries are called conformal infinities. Right? Infinities, conformal infinities of S. So in general, Penrose diagrams are the result of conformal spacetime map, where it's easy to read off the causal structure of spacetime, and where infinities are mapped to finite regions. And we can see that with the simplest example. The simplest possible example. So I said that the targets, so we have a conformal spacetime map F. I said that the target space was usually 1 plus 1 Minkowski, and we're going to try to map 1 plus 1 Minkowski onto 1 plus 1 Minkowski, which means that we have a spacetime T and X, and we want to map it F in 1 plus 1 Minkowski T prime X prime. We can visualize the family of light rays like this, the 45-degree lines. So this would be family U equal T minus X. And this will be the family U prime equal T prime minus X prime. And then we will have the family V equal T plus X T minus X prime equal V. All right, so first we can make sure that we're going to map light rays onto light rays. So the function that we're looking, a conformal spacetime map is a function that preserves relative speed. The function that we're looking for then is something that takes u and returns u prime as a function of u. Let me write it again. Take u and returns u prime as a function of u, and take v and returns v prime as a function of v. And we want this function to be monotonic. So that it preserves order. I don't know. I can. Okay. Preserves order. Okay, so we're looking for a monotonic function and something that would take infinite values of our 1 plus 1 Minkowski onto finite values in our 1 plus 1 Minkowski. And the conventional function that we choose is arc tangent of x, because it's a monotonic function that is mapping infinity plus infinity on pi half. Sorry, just a minute. Yes, so it's mapping plus infinity on pi half and minus infinity on minus pi half. So that's the conventional function that we choose. And now to check that light rays are mapped onto light rays, this is the following procedure. So we said ds square should be mapped on ds prime square equal phi of, so a function of the coordinate square and the old ds square. So let's check that, and I will write light rays mapped by f onto light rays. That's what we're checking. Okay, so we know that ds square is equal to minus dt square plus dx square, which we can write as dt plus dx minus dt, because we recognize the identity a square plus b square, or a plus minus b square, sorry. And now we can write it as dt plus dx dt minus dx, where I've factorized the minus out, because now I can, so this, now I can identify this with du, this with dv. So now I can write ds square equal minus dv du. And to be sure they will be mapped onto light rays, I write that ds prime square should be equal minus du prime dv prime, right? That's a condition, that's what we want to check. So here are u prime, v prime, and here v t plus x and u is t minus x. Okay, I'm sorry that we cannot visualize that at the same time, but let's try to keep it in mind. So it means that we can write minus the f of u du du the f of v dv dv. Okay, and there we see that we have minus du dv, so this I can write it as minus ds square, because it's the result we just found before, and we are left with dfu on du over du and df of v over dv, and this is just a function of the coordinate that we can write phi of x mu, so a function of the coordinate square. So we just check that light rays would be mapped onto light rays. Or good. We can say that Penrose diagrams or conformal spacetime map act locally as isotropic rescaling, and that it can be seen as coordinate transformation, but I don't feel really comfortable with that explanation. But if it makes sense for you, then just know that it can be seen as coordinate transformation. All right. So now, using arctangent to map 1 plus 1, this is 1 plus 1 Minkowski to map on to 1 plus 1 Minkowski using arctangent of x, or Penrose diagram. So our target space, the result of the mapping, will look as T prime, X prime, just 1 minute, please. As a diamond shape, like that. So that's what it would looks like. So this is the target space, 1 plus 1 Minkowski, and everything inside here is the original space 1 plus 1 Minkowski that we mapped onto 1 plus 1 Minkowski. These boundaries are called the conformal. I think I already wrote it, so yeah, and my computer is kind of dying now. I mean, it's not working very good. It's quite slow. Yeah, so the boundaries are called the conformal infinities of 1 plus 1 Minkowski. And we have just mapped all points from 1 plus 1 Minkowski onto a finite region in 1 plus 1 Minkowski. And by mapping light rays onto light rays, the causal structure is preserved. So now we can introduce some vocabulary. So an eternal observer will come from here, and that's his word line, and end up here. And this point is called I minus the past time like infinity. This point is called I plus the future time like infinity. And so you would have to be eternal to come from I minus and to go to I plus. A space-like word line will go from this point to this point and is totally unphysical, but still we can draw it in that diagram. And this is called I naught. I naught. It's the space-like infinity. And then we have these boundaries are called script plus. It's the future null infinity and script minus the past null infinity. And those blue lines, they're given by u prime equal pi over 2. They are the solution of arctangent of arctangent. This is v prime equal minus pi over 2, u prime equal minus pi over 2, v prime equal pi over 2. Right. And yes, you can basically read everything just like we were reading it of normal space-time diagrams. If I go back to my observer and I say that, for example, the observer is at it's this point, then everything he sees is coming from his or her past light cone, and every light he's or she's emitting is going to the future light cone. So that's the past light cone and that's the future light cone, and the observer cannot go that way or that way. All right. So this video was about the Penrose diagrams, the very basics of it. How do we construct them, and how can we read off the causal structure of space-time, and also how we can visualize infinity thanks to Penrose diagrams. And on the next video, we'll be presenting shortly two examples, a bit more handful of Penrose diagram. Okay, thank you for watching.